It is our great pleasure and honor to have you as a speaker of colloquium. And let me very briefly introduce Professor Jungkai Chen. Professor Jungkai Chen got PhD in UCLA under Professor Razarsfeld, and then he came back to Taipei, and he did almost all most important job in Taipei mathematical societies. For example, he's president of Taiwan Math Society and chairman of Department of NTU, and also director of NCTS of Math New Institute, and also currently editor-in-chief of Taiwanese Journal Mathematics. And we encourage to submit good papers. And and for us, he's a central person in NTU side of exchanging professor between NTU and ours. And mathematically, he started from irregular varieties and also very famous work with Professor Heikon about characterization of abelian variety, but in birational sense. And also later expressed MMP for threefold, and then expressed geometry of Q-Pano threefold, and also expressed geometry of threefold of general type, and also geography of threefold. And today he's going to talk, and because by his work he got several awards. For example, Morningside Silver Medal Fellow of AMS and invited speaker of ICM 2018. And today he's going to talk on classification of threefold of general type. So please start.
Okay. Thank you. Yeah, thank you very much for the very nice introduction. Yeah, and it's really my great pleasure and great honor to be here in University of Tokyo here. So my pleasure is that I have many good friends here. So many professors and also some students. So I know many of you. So it's really my pleasure to meet you again here. And also it's my great honor to be here because pretty much of my work is actually influenced by the faculty of the University of Tokyo here. For example, Professor Kodaira and Professor Itaka and Horikawa, Kawamata. Yeah, so there are so many distinguished professors here that influenced the algebraic geometry for the past 3 or 4 decades or even more. So it's really my great pleasure and my honor to present my work here, which is kind of following the steps. So yeah, so I'm going to talk about the classification of algebraic threefolds. So the guiding questions about the classification problem is that we might want to know how many varieties are there. Okay, and also we want to know that is there any constraint of the invariance? And furthermore, we want to understand that more explicit understanding of varieties with extreme invariance. Okay, so at this point, this kind of question is still naive, and I'm going to make it more precise afterwards. So maybe I should make a quotation mark here. Okay, so yeah, so maybe start with let me quickly go through the situation of low-dimensional cases very quickly, and then our main focus will be on threefolds, three-dimensional varieties. So before we started, our varieties, for simplicity, let's considering just projective varieties over complex number C. Okay, so by projective varieties, we mean that varieties are certain subset inside projective space are defined by homogeneous coordinates. Okay, so the first section, let me quickly recall the one-dimensional situation. And in the case of curves, then usually we just classify by genus. So G is the genus of X. Okay, so the usual classification is like this. That in the case of genus equal to 0, then we will see the P1, the project plane, and then project curve. And then in the case of genus 1, then we're going to get some edit curves. And for edit curves, we know that two edit curves are isomorphic. So maybe let me mention that. So given an edit curve, given the complex edit curve, that can be realized as a complex torus. So here C is a complex plane, and lambda is a lattice inside this complex plane, and two edit curves are isomorphic if and only if that they are isomorphic as a complex torus. So from this point of view, then one can really have a more detailed classification. So two edit curves, they have the same topology, but they might be they could be different. They could be different in a sense of complex geometry, or in sense of algebraic geometry, because they could be if your lattices are different, then there are different edit curve, and the moduli can be usually described by so here H denote the upper half plane, and then we have the SL2Z action on the upper half plane. So by considering this kind of quotient, then we see various edit curves. And when genus greater or equal than 2, then we know also we have the modular space which basically parameterize curves of genus G up to isomorphic. And then we know that this modular space has dimension 3G minus 3. Okay, so yeah, so we know pretty much pretty well about the situation one-dimensional, and then also and then we can move on to the case where dimension is greater than 1. Then there's This is a general recipe to understand high-dimensional varieties. So the general recipe is that we can try to study the vibration structures. Okay, so by if we have a variety X, and suppose that we have a vibration, and let F to be the general fiber. So the philosophy here is that we could try to understand the geometry of X from the information of the base variety and also from the information of the fibers. So yes, and so this kind of approach is quite natural appear in the study of high-dimensional geometry. So there are two natural vibrations that we're going to use. The first one is the so-called Ithaka vibration. Okay. So the Ithaka vibration, this is Professor Ithaka. And so how does this work? So usually we should try to start with to consider some functions or some sections, and such that we can produce some map into project space. So the goal is try to find a map into a certain project space, and then let's try to look at so suppose we have something like this, and let's try to look at this image. Okay, so the first thing we can try is that we can try to produce a map into project space. And in order to do this, usually we consider the so-called canonical map. So canonical map, we want to suppose that we have many sections. So this denotes the space of canonical sections. Or roughly speaking, you can consider something functions with zero set and pole set governed by canonical divisors. So intuitively, a divisor is a combination of codimension 1 subvarieties together with some multiplicities. So divisor is a good formulation to describe the pole set, zero set, and pole set. So with this imposed condition, then we can try to search for functions satisfy this given condition of pole set and zero set, and then we can try to search for functions satisfying this condition, and the so among all divisors, there's a most important one called canonical divisor. So this one, this not way too much about how we defined it, but it's should be the most important one, otherwise it's not co-canonical. Okay, so now we have we can consider canonical sections. Then let me denote it, and that image to be, so this is an image. And sometimes maybe there are not so many sections here. So what we can do is that we can try to reduce the condition that by considering the 2 times of canonical, or maybe n times of canonical divisor. So we can similarly consider the 2k or maybe in more general. Okay, so we have the canonical map, bicanonical map, and M's canonical map, and all the way. And what's going to happen is that if we let M goes to infinity, then this is going to be stabilized at a certain point. So we will end up with a model. Let me denote it Y infinity. And this is a beginning of the Ithaka vibration. So this is, we call it but here you might see that I'm still using the dotted map. So which means that it's not necessarily everywhere defined. So in order to make it really the everywhere defined map, then we need to resolve the singularities. Yes, so the Ithaka vibration is actually we should replace this one by certain resolution, or maybe just blow ups, so that we're going to have a honest map from this variety to this model here. So this is a Ithaka vibration. Okay. Yeah. So then we can define the Kodaira dimension kappa defined to be the dimension of the image of this Y. So as we can imagine that this dimension should be important invariance of our varieties. And then we have some more properties that are the most important properties is that the Kodaira dimension of F equal to 0. Okay. Yes. So from this point of view, then we can realize that for the high dimensional varieties, then if we're considering the Ithaka vibration, the base variety has something usually has something of smaller dimension, and in this case, the fiber is something of Kodaira dimension 0. So from this point of view, the building blocks, the most important varieties with okay, so so then in this case, when the Kodak dimension equal to dimension x, which means that this map does not really give you a vibration. It's actually a bidirectional map. So that this Itaka vibration does not produce anything new, but this variety has some special geometry. We're going to talk about that. And the other case that if Itaka vibration is non-trivial, then of course it's quite important to understand what's happened to the fibers and then how fibers varies. So then from this point of view, the study of Kodak dimension, variety of Kodak dimension 0 is also very important. So this part including the study of K3 surface and Calabi varieties, and Professor Ogiso is of course the top expert in this area. And also there are some situations where there's no canonical section, there's no bicanonical section, there's no section at all. So where this kind of approach fails at the very beginning. So in this case, we defined it Kodak dimension to be negative infinity. Yes. So then with this picture and with the Kodak dimension, then if you apply it to the case of one-dimensional situation, then genus equal to 0 corresponding to Kodak dimension equal to minus infinity, and this is Kodak dimension equal to 0, and this is the case where Kodak dimension equal to 1. So Kodak dimension is a very important and nice and invariant in bidirectional geometry. And we can try to apply this kind of trick to the study of surface. So let's see what's going to happen. In the case of surface, so in the case of surface, then okay. So the situation that our Kodak dimension is negative infinity, here we will see projected space, or maybe something like this, or some Hertzsprung surface, or some other dual surfaces. Okay, so we'll see these varieties here, and when Kodak dimension equal to 0, then we have a very explicit understanding of this case. So there we have K3 surfaces Enrique surfaces bielliptic and Abelian surface. Okay, and actually the classification is follow from the further study of another bidirectional invariant called irregularity. So this is called the irregularity. So what I'm going to say here is that when we have a variety such that the irregularity is non-zero, so irregularity measures the dimension of holomorphic one forms. Hold on. So once we have a homomorphic one forms, then we can try to considering the line integral along this one forms, and then we can produce a map to certain abelian varieties. So depending on this invariance, then this class of surface can be further classified into abelian surface or bilateral surface or K3. Yes. Okay, and yeah, so maybe I should. Okay, and when kappa equal to 1, then we know these are elliptic surfaces. So by elliptic surface, we mean there's a vibration to a curve such that the general fiber is an elliptic curve. Okay. Yeah, and the way to see it is just follow from the Itaka vibration. So once you have a surface with quadratic dimension equal to 1, so you considering the Itaka vibration, and this Itaka vibration has one-dimensional image, and the general fiber should be a curve with quadratic dimension 0. And quadratic dimension 0, we know is an elliptic curve. Yeah, so. Yeah, so this kind of vibration idea gives us a very concrete and nice picture for the classification of surfaces. And for the remaining case, actually we don't know. It's not so easy to start from the Itaka vibration, and so for this kind of surface, we just call it surfaces of genotype. So it's quite often that when we encounter something we are not so familiar, then we just give it a name and then pretending we are kind of familiar with him. But at the moment we just know it's surface genotype. But in fact we have more a lot more geometry happening here. So I'm going to show you. Yes. So now it's the right time that I'm going to make the question a little bit more precise. That how many varieties are there up to? Bidirectional equivalence. Okay, so we really want to consider is the bidirectional classifications. So if two varieties are bidirectional to each other, then we should consider them as in the same category. Otherwise, then there will be too many. Yeah, and then we want to study that what kind of condition or constraint of the bidirectional invariance, and then we want to study that what can we say more explicitly for those varieties with extremal invariance. Okay. Yes. Okay. So now let's. So now, for surface of genotypes, then usually we would like to consider the following invariants. So that is Kodak dimension equal to dimension of x. Okay. So usually we want to consider PG. So this is, we also call the genus of X. And holomorphic order characteristic. So this is we want to consider volume okay. Yeah, so before we move on, maybe let me remark a little bit about the Kodak dimension. So Kodak dimension has a property that the dimension of the precanonical sections is okay. So one way to understand the Kodak dimension is that it measures the degree of the growth of the dimension of canonical sections. So if we consider the canonical sections and m's canonical sections, and we suppose that the dimension here is growth if n is getting larger. So if it grows to a certain degree, then this degree coincides with the Kodak dimension. So this is another way to understand the Kodak dimension. And then volume here is somehow try to capture the leading coefficient here. Okay. So we can, and the genus here is nothing but the dimension of the canonical sections. So we can expect that this is kind of the starting point of the sections, and this is kind of the measuring a syntactic growth of the sections. So these two invariants should be related in certain ways, and it's known that they are related let me. Okay. So it's a work by Horikawa that volume is greater or equal than 2 times the genus minus 4 in the case of surface of genotype. So this is a Horikawa. Okay, so this is a first example that I would like to show you that actually there's some constraint there's some relation between these two invariants. So So the volume is always greater than 2 times the genus minus 4. So nothing happening here. So everything should be above this line here. So yeah, I think we should say maybe Nutter and then Horikawa. Okay, so this is called the Nutter inequality. So it's proved by Nutter, and what Horikawa did is that he studied those surface of genotype that satisfy the equalities, and also study the modular space for this kind of surfaces, and not just surface along on the boundary, but also for surface very close to the boundary. So Hayakawa study surface of genotypes on the Nutter line that volume equal to 2pg minus 4 and near the nut. So for example, he also considering this kind of surface and also this kind of surface, etc. Yeah. So this is the example that showing that we actually have more explicit understanding for those varieties with extremal invariance. So for this kind of surface, actually they emit a double covering over a surface over Y over a surface with minimal degree. Or maybe a polarized surface. Okay, so what I mean here is that yeah, so whenever we have a double cover, then we can try to compare the geometry downstairs with geometry upstairs. So there's a ramification formula depending on where's the ramification locus. So and then by so in order to have a surface of genotype, then we should expect that this part should be positive in some sense. So what you can do is that you can try to choose a branch divisor by such that this part just slightly positive in order to have a minimal volume. So whenever we considering the varieties along on the Nutter line or near the Nutter line, then we can consider this surface which has relatively small volume. So in order to have a surface with relatively small volume, then we should have surface which is which is positive but just slightly positive. So just pick this one has minimally possible, minimal degree possible. And then we call it, so if you consider this to be, this line bundle, this is positive, and together with the pair, together with Y, and it's going to be the polarized pair. And so this kind of surface has delta genus equal to 0. So delta genus is the notion has been worked by Professor Fujita, yes, Takao Fujita. Yes. Yeah, and then also we have the Miyaka-Yao inequality here. Yeah, so Professor Miyaka also used to be a faculty here. So the Miyaka-Yao inequality give us the upper bound for the volume. And other than this, we also have another constraint that the volume can be computed as and this is always an integer, positive integer. So in fact, we have another constraint here. Okay, so what we can expect is that we should expect for surface of genotype, the distribution of the genus and volume should sit inside this region here. So, and then for those on the boundary, then actually we know pretty well what's happening here. So here we know that there are double cover, and here we know that there are Borel quotients. And for those with volume equal to 1, there are only 3 cases. And all these 3 cases, we know pretty well what's happening here. Okay. Yes. And now let's move forward to the high dimensional situation, to the threefold case. So to the threefold case, actually similar situation happened. So under some extra conditions. So now let's move on to the so if we consider variety of dimension 3 or higher, then what's going to happen is that the minimum model program is more complicated. And usually, minimum model has singularities. So mild singularities, we mean maybe terminal singularities or canonical singularities or Kawamata log terminal singularities. Yeah, so in high dimensional situation, then we can try to consider the bidirectional geometry, and we want to find the goal for mu model program is try to study the bidirectional equivalent class and try to find a good model inside this equivalent class. And so the good model, one candidate of good model is the mu model, and sometimes we might want to consider canonical model or other models. But usually, even though these good models, we need to allow some singularities. So And so one important category of singularity is a Kawamata log terminal singularity, which is called KOT singularity for short. So now this considering the threefold case, in the case of threefold, then if we assume mu model has Gorenstein singularity, then again we have the Miao-Ka-Yau inequality that the volume less or equal than 72 of all the characteristic. So this less or equal than 72 genus minus 72, something like this. And then in this case, also we have so this is one thing, and the other thing is that we know the volume is a integer. Indeed, it's an even integer. And moreover, we have the Nutter inequality. So now the relations turns out to be something like this. Okay. Yes. So the slope is. So we have a very similar picture, but only the difference is that the slope is different, and also the height here is different, but the structure is very, very, very similar. But this is under the condition that we assuming the Miao model has a Wurtz Gorenstein singularity, so everything is so all the invariants here are integer. So things is it's not so difficult. But if we want to consider in the general situation without this kind of assumption, then we know that there are many examples up here. So the Miao-Ka-Yau inequality does not hold anymore, and furthermore, we cannot expect any Miao-Ka-Yau type inequality up here. And then here we should there are also something here. So for example, we know the volume greater or equal than 1 over 1,680. So this is known. And the known example is where X is a okay. So it's proved that there's an upper bound there's a lower bound like this, but so far we only know that there's an example with this kind of volume. So we are expecting that this should be the optimal lower bound, but so far it's not proved yet. Okay, and somehow surprisingly, the Nutter inequality holds unconditionally. So even without assuming the Miao model has good singularities, so for any threefolds of general type, then it's proved that the Nutter inequality holds. So my previous work with Ming Chen and Jiang Chen, so we can show our previous work shows that this holds whenever genus greater or equal than 11. But then about 2 months ago, then this condition can be removed. So this is a recent work by Chen, Jiang Chen, and Hu Yong. Okay. But here I would like to mention a little bit more about what's happening for varieties along this line, and what's happening for varieties near this line, and what kind of singularity is going to happen here. So one of the theorem. So this is due to Wu Yong and Zhang Tong. Okay, so assuming the PG greater or equal than 11, and if the equality holds, then X emits a double cover over Y, which is a P1 bundle over P2 or principal surface or rational normal square. Okay. So this is one part that we know what's happening if the equality holds. And moreover, if the equality holds, then the mu model has a worse. The mu model is constant. Okay, so that's the first part, and yeah, but if you look at this, then this shows that the volume should be an integer. So, and moreover, this also tells us that the genus should satisfy in that it should be congruent to 1 modulo 3. So it says that for threefolds satisfy the inequality, then the genus should be congruent to 1 modulo 3. So it's not appear for any genus. So genus should be 4, 7, 10, 13, this kind of thing, and so then we might wonder now what happened if genus congruent to 2 or 3, and so if genus congruent to 2 modulo 3, then the inequality is slightly higher than the Norton inequality. So, or maybe just write it as a. So this is. This, and similarly, X emits a double cover over y. But what's happening here is that the mu model has a non-Grunstein singularity. Of type half 1, 1, 1. Okay, so yeah, so this kind of situation appear that in this case the mu model has non-Grunstein singularities, but somehow the simplest non-Grunstein singularities. And similarly, if we considering the case where genus are congruent to 0 modulo 3, then the inequality is something like this. So it's going to be this one, and again it's amid a double covering over certain nice threefolds, and now it has a non-Grunstein singularities, either 2 times of this or maybe another little bit more complicated singularities. But in any case, the mu model is 2 Grunstein. So even though there are some non-Grunstein singularities, but the Cartier index is at most 2. So no matter this one or this one, there are 2 Grunstein. Yes, so yeah. So so finally, I would like to mention moreover that there's it's possible to study study even further, that we can try to study the modular space for this kind of threefolds. So it's possible to study modular space of threefolds on the nutter line or near the nutter line. And the reason is that if genus is higher, then one can embed this kind of threefold into certain let me call it W, which is a P1125 bundle over P1 as a hypersurface. Okay, or one can consider the double covering structure. Okay, so there are several ways to study the modular. So one way is try to embed this kind of threefold into this kind of fourfold. So there's a very beautiful way introduced by Kovlen and Pinatelli. So they consider this kind of weighted producer space bundle over P1. So this is a fourfold, and then we can embed this threefolds as a hypersurface in this fourfold. So the study of moduli turns out to be the study of the hypersurface in this kind of fourfolds. So this is one approach to study the modular space for this kind of variety, for this kind of threefolds. And the other approach is to study this kind of pairs. So this pair. So the branch divisor should sit inside certain linear systems. So Y is for example, could be a P3, could be a P1 bundle over Hertzsprung surface, and then we study some linear system with smaller positivity, and by considering this kind of linear system, then we will see we can produce a double cover, and this double cover turns out to be the threefolds on the nutter line or near the nutter line. So this is another approach to study the modular spaces, and yeah. So I will try to explain more detail of this kind of approach in the workshop this weekend. Yeah, but and then also there's some cases where when genus is small, like for example genus equal to 3 or 4, then they can also be realized as a hypersurface in weighted producer space. So if genus is so the X is a okay. So for some special case, we can also realize as a hypersurface in weighted producer space, and then we can study the moduli for this kind of hypersurface. So there are some possible approach for the study of the modular spaces, and also thanks to this kind of very explicit understanding, then we can also study the other invariants, like for example the fundamental group are known to be trivials. This kind of result can also be obtained. But then the next challenge we'll try to see what's going to happen for even higher dimensional situation, for example 4-fold or n-folds of genotypes. Then what can we expect? And yeah, and then there are yeah. So there are still many interesting problems around this area. So I think I stop here. Thank you very much.